Okay, in this example we have two blocks, A and B, which have their own distinct mass. They're constrained to move along a smooth vertical and horizontal guides, as shown in the figure. We're told that blocks A and B are connected by a lightweight rod of a given length, and that a force, F, is applied, jumping around a little bit on you. A force F is applied that acts to the right on block B, and we're told furthermore that the position where SA is equal to 1.5 meters, A is moving downwards with a given speed. Based on all this, we're asked to determine the acceleration of blocks A and B at this instant, and also the force in rods A and B. Okay, so as in all kinetics problems, the way I'm going to start this is by sketching free body diagrams, in this case for both blocks separately. So if I start with a free body diagram for block A, maybe I should designate this as A like so, I'm going to have here a normal force, which I'll call NA, between the wall and the block. I'll have the weight of this bar, which it will be simply MA times G, and I'll have this force FAB, which will be oriented at an angle theta with respect to the horizontal, where theta, and I'll write this here off to the side, could be rewritten as, in this case we know the length of the rod L, and we know the numerical value for SA, I believe. Let's go back up and check that. That is indeed the case. So we have the opposite over the hypotenuse, so we know this is the sine inverse of SA divided by L. And in terms of acceleration, we know this thing can really move up or down. I'm going to choose to do this upward positive, so this will be MA times AA. And I'm going to use everything here in terms of an XY coordinate system. If I look at block B now, in terms of forces, I'm going to have the applied force F. I will have an equal and opposite force FAB, which again will be oriented in an angle theta with respect to the horizon. I'll have the weight of this particle, which of course will be MB times G, and I'll have a normal force between it and ground, which will be NB. And I know this particle is constrained to move horizontally, so I'll have some MB times AB here like so. So I'm going to start now by doing the kinetics associated with this problem. So I'll start by summing the forces in the X and setting this equal to the, well, in the case of block A, actually 0, because we know it can't accelerate in that direction. And if I do this, what I'm going to end up with is that FAB times the cosine of the angle theta minus NA is going to equal 0. Let's call that equation 1. If I sum forces in the y direction on this block, I know this is going to equal MA times AA. And if I do this, I'll have FAB times the sine of the angle theta minus MA times G is going to equal MA times AA. Let's call that equation 2. If I adopt a somewhat similar procedure with block B, I'm going to have summing forces in the x direction is going to equal MB times AB. And if I work this out, I'm going to have F minus FAB times the cosine of the angle theta is going to equal MB times AB. Let's call that equation 3. And if I sum forces in the y direction for this block, I know that's going to equal 0. So I'm going to have NB minus MB times G minus FAB times the sine of the angle theta is going to equal 0. Let's call that equation 4. So if I look at equations 1, 2, 3, and 4, let's count our unknowns. Well, I don't know the force in the rod. I don't know the normal force on the wall. I don't know the acceleration of block A. I don't know the acceleration of block B. And I don't know the normal force with the ground. So we have here 4 equations and 5 unknowns. It begs the question where we could get the following equation that we need. The answer here is actually going to be something that we talked about early on in this class. We're going to get that answer from kinematics. In the case of this problem, I know, for example, that there's a kinematic constraint. If I look at the constraint in particular, it's the fact that these blocks are connected by a rigid bar. That means that we have that SA squared plus SB squared is equal to L. We can call that equation 5. That would give me a value for SB given the information we're given about SA and L. And by the way, I should say this is L squared. But that doesn't help me out here by giving me an additional equation. Actually, we've basically just add an additional equation and an additional unknown. However, if I take the time derivative of equation 5, what I'm going to get now is the relationship that 2 times SA dot plus 2 times SB dot is equal to 0. Let's call that equation 6. Again, we've added an additional equation, but we've added an additional unknown, in this case being SB dot. Let's take the derivative of equation 6 and see if that helps me out. If I take the ddt of equation 6, what I'm going to get is that 2 times SA dot squared plus 2 times SA dot, SA double dot, plus 2 SB dot squared plus 2 times SB double dot is equal to 0. This is actually very useful for us. From equation 5 we know SB. From equation 6 we know SB dot because we're given SA dot, that is we know the speed of block A at that instant. So we can solve for SB dot, and if we take that and plug it into equation 7, noting that SA double dot is equal to the acceleration of block A and SB double dot is equal to the acceleration of block B, we've now added an additional equation without adding an additional unknown. So to solve this problem, we're going to take these 7 equations and 7 unknowns that we have, and we're going to solve this thing all out. And if you do that, you're going to recover not only the acceleration of block A, one of the things we're asked for, the acceleration of block B, another thing we're asked for, but also the force in member AB, the final thing we're asked for. I'll leave it up to you to solve the system of 7 equations, 7 unknowns. I promise you it's not as bad as you think. Take care, everybody.